Assalamualaikum warahmatullahi wabarakatuh. InsyaAllah, today's session will be regarding chapter number 3, superposition and standing wave. Right, what is standing wave? Standing wave in reality is another name meant for resonant. So they give you this guitarist Jack White, where he use up the resonant situation so that sounds coming from the string would be amplified. Now, first and foremost, we need to understand the basic concept, which is superposition principle, or what we call is interference. What is interference? Based on your book, it says that when you have two or more wave traveling in one medium, the resultant value of the wave function is the summation of the two waves together at that position. Means if two wave individual have five amplitudes and another is 10 amplitudes, so the net would be 15. Right, so we can divide it into two categories. Number one, constructive, it means that it's adding up. Disruptive, it means that it cancel out. In what case? Okay, let's say that we have two waves traveling towards one another. Okay, and then this is a case where constructive occurs. Okay, constructive occurs where they meet up and you find the resultant during the interference or during the superposition. The resultant amplitude is summation of the individual wave, summation of the individual amplitude. So this one, the summation. When they are considered as disruptive, you find that the amplitude decrease, okay? And that's considered as disruptive, as simple as that. So again, ask yourself, what is disruptive? When they overlap and they cancel out one another. When they overlap, the net resultant would be less, okay? What is constructive? When they overlap, when they interfere, the resultant would be larger than individual. Alright. Let's now look at, this equation, I'm not going to derive yet, but I will spare, inshallah. Let's have a look at how things progress, okay? Now, this equation is actually coming from the idea of two waves traveling, and when they combine y plus y, you have this expression. And by combining with trigonometry identity, we are simplifying it into this expression. So at least you can understand. All right. From this expression, okay, let me rub off. The trick to understand this expression is this is actually amplitude. This is amplitude. Therefore, you are looking at like this expression quite similar to something you have seen previously. Why? Is A cos something or sine something. Okay, but this topic they are using sine. A is sine kx minus omega t, and this is the function sine kx minus omega t, and I forgot about the phase difference. And in this case we have phase difference, which is okay. All right. Okay, therefore 2a cos 5 over 2 is the amplitude, understand? Okay, in the case where we find that the most or the largest amplitude possible is 2a, the largest possible is 2a, that will give us the situation that the product of cos in the bracket should give you equivalent to 1. Okay, and for that to occur, therefore, the angle need to be a product of, okay, right, hold on. That's the idea that we're going to look at, which is this one. So when constructive occurs, therefore, the cos 5 just now is positive or negative 1. Okay, that's something that I have said just now. And therefore, the angle need to be in a form of 0, 2 pi, 4 pi. So constructive, let's simplify. Constructive, when 5, then you will find that the angle is either 0, 2 pi, 4 pi, 6 pi and adding on 6 pi, 8 pi, all are in the multiplication of 1 lambda, 1 cycle, all in the multiplication of 1 cycle. Okay. Now, how about destructive? Destructive, let's have a look. Okay. S5 is 180. How did they arrive with this value? Okay, it's just do the reverse. If it's the maximum, so constructive adding up and maximum value is 2a, therefore cos pi need to be 0 to pi and such. Okay, so we did the same process to cos just now. So cos pi need to be equivalent to 0. And when it needs to be equivalent to 0, by substituting 5 as equivalent to pi, so pi divided by 2 will give you 0. And in short, okay, it's just pi, 2 pi, okay, 3 pi, okay, 4 pi, no, 5 pi, okay. And that is what it tried to say, that it's an odd multiplication of pi. Okay, okay, now let's do an addition. Okay, before I proceed, let's look at this figure. Look at the 5 difference, it's 0. Now, when it says 0 here, 0 is represented as pi here, 0 angle, okay? And you will say that they are in phase. We also name it as in phase. In daily life, we can see this similar to your and your friend. Now, imagine you and your friend going to the bazaar, walking side by side. So when your friend, he was using his right foot, you are also using your right foot. That is considered as in phase. In sounds or in wave, in wave, if the source is emitting crest, then the other is also emitting crest. If I'm up, you are also up. If I'm down, you are also down. So we are in phase, always together. But out of phase is always like opposite to one another. So opposite to one another, we can observe at figure B. If I'm up, then you are down. Understand? All right. And differences in phase is 180. Okay, let's look a little bit higher. Now, you have learned this in high school. Example given, for example, you have two source. This is speaker, stereo, okay, speaker. Okay, speaker 1, speaker 2, source 1, source 2. Never mind, they are emitting source, emitting sound, okay. There will be another version where coherent sources and such. Okay, basically, most of the time, it's supposed to be coherent, okay. Now, what happened is, as the source sound travel to him or to you, the question is usually asking, oh, should this person be hearing constructive or destructive? So what did you do? From high school, you are taught that let's find the difference of R. So R1 minus R2, R1 minus R2, where we call this as delta R, and we divide with lambda. We divide this path different with lambda. And when we divide with path different with lambda, if the value is equivalent to 1 over 2, 3 over 2, okay, or rather than have lambda over here, denominator, I brought it to the right. So that, why? Because to make sure that it's equivalent to what's given in the book. Lambda over 2. Okay. Now, so if let's say it's over 2, it's not even a complete cycle. Cycle is half of it, which you will find something quite familiar to this. This one is actually resembling the idea of 5 equivalent to 180. Where 2 pi is divided by 2 pi. Dapat pi. Remember just now? So this is what the book trying, this it says that, and for odd, when this happen, this is actually a case where destructive occur. So now let's just hold on. So delta R equivalent to lambda divided by 2 and then n is equivalent to 1, 3, 5, 7, 9. So this is as long as the lambda is half and get half, you understand? A odd number. It is not a complete cycle, destructive. And it also makes sense for constructive that path difference should be equivalent to a lambda itself, one cycle of lambda. So one cycle of lambda become, depends on the book. Okay, let's me cross check whether the book is using, yeah, okay. So this is the one, n lambda, all right, n lambda. So this is n. So meaning a multiplication of a complete cycle. Perkali multiple of complete cycle. 1 lambda, 2 lambda, 3 lambda. Okay. So 1 lambda is 2 pi. 2 lambda is 4 pi. 3 lambda is 6 pi. So n is 1, 2, 3, blah, 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 blah. Okay, easy to remember and understand, yeah? Okay, this example is not in our syllabus, so let's have a look at our, all right, so 17.2, 17.3, 17.5. Standing wave, right? Standing wave. What is standing wave? Standing wave is another name to represent resonance, yeah? Now, however, standing wave is also called as a stationary wave. Okay, or sometimes it called, the book represent here as stationary outline. If you go and look at other references, they call it as stationary wave. Why is it that it's called as stationary wave? This would be very helpful. Okay. Okay, this is 0.53. So he is sending wave by using this vibrator. So the wave traveled on the string, through the string, and then sent to another pole here, and then it get reflected. Never mind. Okay. But what I like you to see is, the traveling wave, there are two traveling waves that overlap with one another, interfere with one another in this figure. And you find that, okay, he is obstructing. Okay, you can't distinguish the individual wave anymore. You just simply see the pattern, but you cannot see the wave from coming and incoming, whatever. The individual wave is not there. So as if it's stationary, okay, and standing up. Okay, some say it's stand up, standing up. Okay, standing wave. Right, let's get back to the book. Okay, in standing wave, we need to learn the character, the shapes. So the shape can be categorized into two, anti-knot and knot. What happened during anti-knot? The wave are added up and constructive occur. Constructive occur. So this is where constructive occur. And the knot is where disruptive occur, right? Nodes is used in biology as well. Nodule, okay, where it just look like nodule. Shapes is like kecil, bulat, and doesn't move, okay? Nodule, nodes, right? Now, in this topic, it's quite important to understand and calculate where would these anti-knot and knots be. So I'm going to help you. You can do your reading over here a little bit on your own, but I'm going to focus on the very core idea of how to calculate. Okay, individual wave, okay, is like this. And when you do such, you have such, this figure. And therefore, this is 1 lambda, 1 lambda. All right. And the amplitude can be calculated at any position based on the expression earlier. Okay, hold on. We are not there yet. All right. So therefore, you will find that if this is pi, and therefore, half of it would be if this is lambda, half of it would be lambda divided by 2. Lambda divided by 2. And this anti-node and nodes, okay. So this node is there at lambda divided by 2, while anti-node is lambda divided by 4. 1, 2, 3 section, 4 section. Can you see that? So we will divide it into 4. Then you will find anti-node will be at the position 1/4 of a cycle, while node will be half of a cycle. And that's how it comes upon this expression, that where is nodes? Nodes is half of a lambda. Half of a lambda. And then it's here. Another lambda. Okay. So it started here. And then another 3 lambda over 2. Okay. So it's always like lambda divided by 2. Lambda divided by 2. And let me complete this so that you don't get confused. So this lambda is actually lambda divided by 2, but we are substituting n that's equivalent to 2. So becomes 2 lambda divided by 2. Simplified become lambda. Understand? So the generic become n lambda over 2, or general expression become n lambda over 2. This is something that you need to memorize and correspond to the nodes. How about antinodes? Just now we can see that it's lambda over 4 and lambda over 4. The first one is lambda over 4, and then repeatedly you will find that at 3 lambda over 4, 5 lambda over 4, and therefore the generic become lambda over 4, but you must ensure that n is 1, 3, 5 and such. Okay, and again, this is something that you must take serious consideration to remember. Now, in conclusion, a generic conclusion, distance between adjacent bersebelahan, next to one another, nodes to antinodes, the one that we have discussed just now, antinodes. Let's look at it from here to here. Okay, from the nodes to the next nodes is actually half a lambda. Half a lambda. Why did I say such? Can you see that we divide by 4, this is 2, right? 2 divided by 4 is 1 over 2. So it's half a lambda. Half a lambda. While distance between adjacent node is also half a lambda, but between nodes and adjacent antinode is lambda over 4. This has been described earlier. Antinodes, nodes. Antinodes, nodes. A quarter of it. So you must learn how to sketch it and also how to identify where is node and antinode. Okay, sketch and label. Sketch and label. All right. Okay, let's have a look at the first example here, 17.2. Two waves traveling in opposite direction, like such. Produce a standing wave. You can see the opposite here. This is to the right, this is to the left. Individual wave functions are as given. Find amplitude. Okay, amplitude. Now, you might be tempted to just put 4 plus 4, but that's not going to happen. Okay. So what it says that when it's located at x 2.3 centimeters, so they have traveled some distance away, and you would like to know at that location what will be the overall amplitude. All right. Now, how to solve? Okay, how to solve? You will find here. Okay. Since we are interested to find amplitude, okay, keyword is amplitude. Amplitude is the largest, and therefore that should give us cos omega t, the value of omega t, the largest as well, right? And that's okay. We can skip this one. Okay, no problem. Okay. Find the amplitudes. Okay, since what you can do is just substituting 2.3 centimeter. Okay, and effect of 2t here, we do not want 2t here to interfere into our calculation. Okay, and before that I forget. Okay, I forget that the idea is the two individual waves need to be interact with one another, and therefore we need to create the new equation, and the generic new equation is 2k 2a sine 2a sine kx cos omega t. And substituting into this generic equation, you find 4 plus 4 8, okay, centimeter, sine 3x cos omega t to t. Right now, okay, this is what I'm jot down just now. I simply forget. Okay, since we are talking about amplitude, then we have to ensure that this product of cos omega t has to be the maximum value, and maximum means that equivalent to 1. Okay, maximum equivalent to 1, and therefore leaving our option is just 2a sine kx, 2a sine kx. Okay, and 2a sine kx will give you, substitute the x as equivalent to 2.3, 4.6 centimeter. So we are not dealing with the time because we are interested to find the amplitude at that location. Now, find the position of nodes and antinode if one end of the string is at 0. This is okay, alhamdulillah, easy to remember, okay, easy to understand. Okay, so equation given earlier that nodes itself is n lambda over 2. So as simple as that, what we did is we need to substitute the value of the lambda. And where do you get the lambda? The lambda had to be taken from the k just now. K just now. What is the K? K is 3. So this is what they did just now. K is 3. K is also equivalent to 2 lambda over 2 pi over lambda. Sorry. And lambda is 2 pi over 3. So that's what you did. You substitute the value into the expression and you create the generic. Okay. The generic expression. Okay. Might be tak nampak madam. Okay, let's have a look. Let n stay as n. Lambda is 2 pi over 3 and then divide by 2. So sorry, color. So you find you can simplify. So that's how you arrive with n lambda over 3, and you must ensure that n is 0, 1, 2, 3, the generic sequence that been given earlier. Okay, and then for antinodes, repeat the same process of n lambda over 4, n lambda over 4. Okay, 1, 3, 5, 7. Easy to remember, yeah? All right, let's have a look at the next subtopic, boundary effect. This is our next subtopic before we went for break for this video. Boundary effect, reflection and transmission. Okay, we have two. Number one, we call it as fixed end, and second is we call as free end. Okay, free end. All right, free end. Okay, when when a wave travel and meet with a fixed end is almost like a wall. So concept of a wall ataupun a mirror is the reflected will be in the opposite direction. So it will be inverted. This is what it tried to say, inverted. While if it's traveling at the free end, so free end there was no impact using Newton's third law. So you can also embed the idea of Newton's third law. There was nobody to make you bounce in the opposite direction. Therefore, it will not be bounce. It will go back and travel in the same phase. Kita panggil same phase. Okay, same phase of the incoming wave. Same phase. Okay, my guys. Because the word is not used in the book. This is same phase. Okay, and this is inverted phase pun boleh tak? Alright, or downwards. Alright. Let's look at this video to understand it better. Okay, this is free end. Okay, let's repeat. Look at the wave. All right, you can see at the boundary, it goes to the maximum amplitude and then travel in the same phase, upright, remain upright. Okay, the wave is now traveling. Let's go back a little bit. Yeah, it gets reflected in the inverted direction. And then later on get reflected again. So you have, in this case, as if there are later coming, will later meet up with one another. Okay, and at the end of the day, this is the basic concept. Sorry, fixed end just now would be the basic concept of creating what we call resonance on string. Okay, is there anything else? All right. Okay, this is a case whereby you have two waves traveling, passing through one heavier or higher density, and you can see that amplitude slightly becoming less. Okay, slightly becoming less. So, sorry, this is not the case. This is a case whereby because it is higher in density, the wave get reflected and also some would be transmitted. Some is so energy gets separated lah. Energy gets separated. Some goes backward in the opposite direction. Some travel onward, yet reduce in the amplitude. Okay. This is the case, and a bus, figure 17.2, a bus traveling to the right on a heavy stream approaches a junction to a lighter spring and situation after the reaches the junction. Okay, so you still see that there is situation of reflection. Still, reflection is observable. Okay. Keyword in the book: when train travel heavy stream, strike the boundary. It get reflected. Part of it reflected and part is transmitted. Transmitted means travel onwards. All right. Okay, I promise you this would be our last, but I'm still interested to discuss with this one. This is our first resonance model with on a string. It must be done. It must be done with fixed end. Fixed end. Fixed end. Both ends. All right. So therefore, a single wave, a single disturbance is enough to send wave, and then we have two waves later on that will interfere with one another. One is coming in the upright version and the other is in the inverted version. If the frequency is right, that match with the resonance, then you will find it will exhibit what we call as standing wave or stationary wave. Okay, now our observation from this experiment, okay, it will look something like this. This is what we call first harmonic. Okay, frequency that used to create this resonance is called as first harmonic or fundamental. This is second, easy to remember because two loops. Okay, two loops. Right, this is the words loops. Okay, and this is three loops, and therefore third harmonic. Okay, there was another name to call it: fundamental, first overtone, second overtone. Okay, but it's not described by the book, so don't worry. They will ask question only what's inside the book. Okay, term use would be only term used by the book. All right. Now, how did they? Okay, hold on. Remember the speed of wave, V is F lambda. Okay, this is the one that we're going to use, F lambda. They rearrange so that F is V over lambda. The aim is to get resonant frequency or we call it as natural frequency, both the same. Natural frequency or resonant frequency refer to the same thing. All right, V over lambda. Now, have a look at the single loop just now. This one, or okay, can. This one. If we complete it, okay, and therefore the length just now exhibit only half a lambda. Understand? The length exhibit a half a lambda. So therefore, a lambda is equivalent to 2 length, twice the length of the string for the first harmonic. So they substitute into here 2L. Okay, and okay, I like to produce how to get the expression. Will I? Okay, let me show you how to get the expression. For this one, it's quite simple, so I can show you. Now, let's have a look for this one. This is a case where lambda is equivalent to the length of the string itself. This is a case whereby this is the lambda. Okay, so how many lambda do you observe? 1 lambda plus half. 1 lambda plus half. So 1 over 2 lambda plus a lambda becoming 3 over 2 lambda. So this one. So simplifying, you will find that the lambda is equivalent to 2L over 3. 2L over 3. Now, so you find the expression of 2L will later on be repetitive. So since it's a repetitive, you can generate a generic equation. You boleh buat equation general, and that's the reason why becoming as such. V over lambda is 2L, and then you modify the n. So long if n is 1, then that will be the first one. Understand? So when n is 1, that will be F1, referring to the first harmonic. If n is 2, then referring to the second harmonic, third harmonic, fourth harmonic, and goes on. Understand? All right. Now, from previous topic, you have seen this expression that speed on wave on a string is tension over mu. Okay. So aside of this expression, so it can as well be NV over 2L, or the V is being substituted with tension over mu. Still remember what is T? T is tension of the string. Mu is linear mass density of the string. Linear mass density of the string. Okay. Linear mass density of the string. Yeah. Okay. And therefore, fundamental frequency. Fundamental is the lowest frequency. Would be number 1. Just substitute N1 into this expression. 1 over 2L square root tension over mu. Understand? Okay. Now, from this expression as well, you will find that you can as well factorize it. Okay, when this is 2, okay, this is 2, you will find that F2 is actually 2 times F1. I'll give you an example. Let's say example, F1 is 30 hertz. Therefore, F2 is 60 hertz. F3 is times 3, 90 hertz. Yeah? Okay. So the harmonic series, that's why it called as series, because it's multiplication of the first one. All right. Give me a C notes. All right. Now, example 70.3, the middle C string on a piano has a fundamental. Okay, the trick is, it doesn't say that this is number 1, but fundamental is number 1. Yeah? And the string for A above C has a fundamental frequency as 440. Calculate frequency, the next two harmonic of the C string. Okay, C string, let's focus at 440. 2 harmonic means the next. So 440 times 2, okay. Right. Where is it? And above C, I get it right. Okay. Oh, middle C string. Sorry. We have to reread the question once again. Okay. The string itself, the string is the string. Okay. The middle C string has a fundamental 262. Okay, let's focus on this. So calculate the next two harmonic of this string. So 262 times 2 and also times 3. The next two. Okay, so which is F number 2 and also F number 3. That's it. Okay. Now, if A and C, all right, and the string for A above middle C has a fundamental frequency of 440. Okay, hold on to that. If A and C has the same linear mass density, determine the ratio of tension in the two strings. So there are two strings, okay, which is number 1 C, and then the other is A, I think, okay, A. And they have difference 262 and the other is 440. So what did we do? We use the common expression that I teach you earlier, okay? Expression divide with the expression. So this is what they did. F divided by F. So you will find this expression if we even book up properly. It's supposed to looks individually like this. And therefore, when you divide with one another, you can now cancel out the effect of 1 over 2L and leaving only, okay, let me show you properly lah. It's just unfair to leave it as such. 2L, this is TA over mu, 1 over 2L. This time around, it's tension in the string, C divided by mu. Okay. Now, since they say that has same linear mass density, so these two value can later on be cancelled out. Or what should be happening is TA over TC square root. Oh, not enough space. Can I just jot down here? TA over TC. So everyone is a square root. But you will find that up here as well, 1 over mu square root as well, and divided with 1 over mu square root. So that's the reason why you can take away 1 over square root mu and leaving it as such, and then simplify them, solve with F, you are going to get 2.82. Okay, so means tension A is larger than C by 2.82. All right, that's it for session today. Thank you very much.